right, good morning, everybody. Let me upload the the documents for the day in the chat right quick. I'll wait for my iPad to boot up.
All right.
So you should see two documents in the chat, and so the one of them is like a compilation of all the reactions we're gonna cover, and the other one is what we'll be working off of. So we're just gonna go through the compilation sheet first, and then we'll start working on the reactions after that. Give me 1 second. All right, let me hope this is not a bad tech day. Come on. All right, let me share my screen right quick. And my mic is acting stupid, so if it goes out, just put something in the chat. Let me know if you can't hear me. soon as it comes up, we'll get cracking. So on this sheet right here, this is like the last set of reactions that we're gonna be covering. So you'll see up top, I kind of have it organized by the type of reaction, and you see here you got so up top at the very top reactions of alcohol. So we're gonna start there, and then basically take the alcohols all the way from alcohols to carbonyls, and then from carbonyls to reactions of carbonyls, and then we're going to talk about amines and how they react, and that's in that bottom right quadrant. So the first set of reactions are going to be here, right? Just reactions of alcohols, and there's really only 3 reactions. 2 of them we've kind of seen already with the esterification, and then the last one is ether synthesis. So we're going to start. Where the heck did that 36 come from? I don't know. Let's see if I can get rid of that. We're going to start at the top with the 2 esterification reactions. So I'm going to cut these out. And paste them on a new page. And let me edit this part out too, because that should be HCl. All right. All right, so for the top reaction, that's just a simple transesterification, and we've seen that before. When we made aspirin, this is a similar type of reaction. Right, so in general, if you take a carboxylic acid and an alcohol, we'll just say R2, and react them together, heat them up. Normally, you do this in the presence of an acid, some type of acid, to activate your carbonyl. The resulting product is a ester, and then you lose water as a side product, right? So that's what transesterification is. You can see up top, it doesn't matter what the alcohol is, you just need a acid catalyst and you need to heat the reaction up, right? So again, we're talking about reactions of alcohols. So one of the main reactions that alcohols participate in is esterification. So the way this works, we're going to look at the mechanism for this and for the acid chloride route, because the acid chloride is a little more facile because of the chlorine, right? So we're going to look at both. So the way that this works, so this is, and let me back up. This is what you're looking for when you're trying to predict products. You're looking for the carboxylic acid group. And this is the point in the class where if your functional groups are rusty, you need to refresh. I mean, now I don't know any other way to put that. You gotta know your functional groups. So that's your carboxylic acid, and then your alcohol. This is what you're looking for. So when you see these 2 things together, you know that there's going to be a transesterification reaction. All right, so how this works, if you recall from when we did Grignard reactions and we had like the Grignard itself was a nucleophile, and then when you added a nucleophile to the, when you added it to a carbonyl, it attacked the carbonyl carbon, right? So 99% of the time, your carbonyl is going to act as a nucleophile, right? So the way that this, I'm sorry, as an electrophile. So the way that this works is you take your carboxylic acid and the H plus is just to activate it. So that's going here, right? That carbonyl oxygen is going to pick up, do proton transfer, and that activates the carbon because now when the oxygen has a plus charge on it, it's gonna increase that dipole moment between the carbonyl carbon and oxygen. So this is now OH, and now my alcohol can come in and attack. So R2OH, right? That's gonna come in here, attack your carbonyl, right? And this is not anything we haven't seen before, right? So that comes there, attacks, and then you end up with what's common to all of these carbonyl addition reactions. Let me move this down here. You end up with a tetrahedral intermediate, and we've seen that before. We've actually seen that when we did the Grignard addition to carbonyls, and that's a common intermediate to all carbonyl reactions. They all go through that tetrahedral intermediate. So this is now here, OH. All right. So this is the tetrahedral intermediate that's going to break down and eventually give you your ester. All right. So if I want to lose water, what do I need to do in order to lose water as a leaving group? In this molecule right here. So I'm gonna pick this OH group. This one right here, I'm gonna use that. If I wanted to lose water, I need to do a proton transfer internally or intramolecularly. So I'm gonna take that oxygen right there and pick up this proton. Right, so that's gonna give me a water molecule there. Like so. And so now I just need to force that water out. Let me switch modes right quick. All right, so once I do that, I'm almost home. I have this. And that's still protonated. Like that. Plus water. And then whatever my acid is, that conjugate base is what's going to come back and take that proton off of your off of the ester and give you the product. So that's that plus water plus HX, whatever X is, right? Because whatever your acid is, let me not say X, I'll say HCB, right? That whatever the conjugate base is of your acid from here, that's what's going to come in and remove that proton. I can put that down here. All right. Any questions about that reaction? So that esterification is, if you know the nuclear, everything that we study in this section is going to be based on stuff we already know, right? It's all nucleophile, electrophile chemistry. There's nothing new. The application is new, but the chemistry itself is not new. So everything we study from this section is going to be some type of nucleophile, electrophile chemistry, right? No radicals, no nothing. All polar reactions and all nucleophile, electrophile chemistry. All right, questions about the transesterification? All right, let's look at the acid chloride reaction, which is going to be similar, but it's not identical. So with the acid chloride, your carbonyl starting material is going to be different, right? It's not going to be a carboxylic acid. So you're going to start with a acid chloride. Right? This is way more reactive than a carboxylic acid. So you don't need uh you won't need like acid catalyst or anything. The acid chloride is so reactive that even when you open the bottle and expose it to air, it's already reacting with the water molecules that are in the air. So it's very much reactive, more highly reactive than a carboxylic acid. So that's the advantage of using it. So we're going to use the same alcohol. All right. So somebody tell me what the first step is here. I have a carbonyl and I have a alcohol together. The alcohol is my nucleophile. The carbonyl is my electrophile. What's the first thing that's going to happen?
OH is going to attack the carbonyl.
That nucleophilic attack, right? That's the first step. Your carbonyl is a great electrophile. And it's that carbonyl carbon, because of that dipole, it's going to be open and susceptible to nucleophilic attack. So from here, I'm going to get this tetrahedral intermediate. That's that. And this is going to be O. That's positive, right? And then here now, I'm just going to eliminate and kick off the chlorine. So now I have this second intermediate plus chlorine, Cl minus, and then that's what is going to come in and remove, do proton transfer with that OH group. So that's coming here like that, boom, and then you have your ester. Much faster, much more efficient, because your carbonyl star material is more reactive. So it's that plus HCl. So I need to fix that. I thought I already did it right there. I need to fix that up here. And you can fix it on the handout too. The handout is in. I posted it in the chat. And I can do it again. Let's see if I can bring the chat up. So the first link, or the first PDF, is the sheet, the compilation sheet with all the reactions on it, and then the second one is going to be our worksheet that we're going to work through for the next until we get to the last day of class. Here. All right, so if you didn't get it when I posted it the first time, you can grab it now. All right, so the other alcohol reaction that's up top that we're going to look at is this Williamson ether synthesis. Right, it's a fairly simple reaction. It's like a SN2 type reaction, which again is something that we've seen before. It's not, it's nothing new. So let me go down to here.
Dr. Russell, can you go up a little bit? Okay, I got it.
All right. So with the Williamson ether synthesis, that's exactly what it is. You're making an ether. Oh, sorry about that. You're making an ether from an alcohol. If you remember your functional groups, an ether is a molecule that looks like this, right? Where both of those R groups are alkyl groups or carbon-containing groups. And so if I take an alcohol, I'm gonna take the one we have up top. I think that's it. And I treat it with an alkyl halide. I'm just gonna say RX. So I have an alcohol halide, and I need a base. So normally it's like sodium hydroxide or KOH or something like that. And then my product is an ether plus water plus whatever that halogen is on my alkyl halide and sodium, right? Because remember, sodium is always going to be +1. And so When I lose that halogen as my leaving group, that's going to automatically form a salt with sodium. All right, so the purpose of the base in Williamson ether synthesis is to remove H plus from OH. Right, so the base takes off a proton from the alcohol and makes it a better nucleophile. So that's the first step. And let me just show the hydroxide. So that's negative, that's gonna come here. And I need to draw that out. All right, so the hydroxyl of the sodium hydroxide is taking off that proton from oxygen. Oh, too many carbons. So now we have this, and this is my nucleophile. And then obviously from that we'll make, we have water. So that's my nucleophile, and now I'm going to react that with my alkyl halide, right? And from here, this is my electrophile. From here, it's just an SN2 type substitution. All I'm doing is taking this as my nucleophile and attacking here and losing that halogen as my leaving group. And I'll put the sodium up here too, because that's going to form a salt. Anytime sodium is in the solution, if there's a negative, if there's an anion in solution with it, it's going to form a salt with it. So now once I attack the electrophile and lose my leaving group, so now I have my ether, which is my main product, right? Plus water, plus, again, when I lose that leaving group, it's leaving as X minus. It's going to leave as a negatively charged atom, right? So then that's where my sodium comes in. It's going to just form a salt with it. Right, so again, this is not anything new. It's all stuff we've seen before. It's just a different application. We've seen nucleophiles and electrophiles. We've seen substitution. We've seen elimination. All those esterifications are elimination reactions, right? Addition followed by elimination. And then the ether synthesis is proton transfer followed by substitution, right? This is stuff that we already know and we've already seen. So there's nothing out of the ordinary. All right, questions about anything we talked about so far? All right, so let's go back up to that. Actually, you know what? Let me do this. Let's go to this handout, which is in the chat. If you want, it's also on Blackboard. Both of these documents are on Blackboard. So if you look at the reaction wheel up top, like it's a bunch of different reactions, but we're going to look at this one right here. Right, you can see automatically you have a alcohol present because we're talking about reactions of alcohols, and then you're going to treat that with sodium hydroxide and methyl bromide. What you also see, there are other functional groups here, but this set of reagents, the sodium hydroxide and methyl bromide are specific for that alcohol. They're not going to react. You know, the benzene ring is not going to react, right? There's no catalyst So we're not doing any type of Friedel-Crafts reactions on that. And then for the alkene, that's not going to react because there's not a set of reagents that will react with an alkene. So when you see the alcohol in the presence of a base and an alkyl halide, it's immediate. It's an immediate. Well, it will be. It may not be now because this is brand new to you. But you need. My suggestion is to take that uh, drill sheet with the quadrants on it and make you some flashcards. So when you see these reagents, you'll recognize them. So this will be the conditions for a Williamson ether synthesis, right? So what would be the product of that? Not the mechanism. We're not pushing arrows. I'm asking strictly for what the product would be for that reaction of that alcohol with sodium hydroxide and methyl bromide. We know the product is going to be an ether, right? Because the reagents are telling us that those are the reagents for ether synthesis. So we know it's going to be an ether. We just need to know what the product is going to look like. All right, so one kind of, I know I don't teach shortcuts, but this is not really teaching a shortcut. But one way to think about this is, it's a type of substitution. So on the oxygen, we're going to substitute, and this is just a way to think about it. We're going to substitute the hydrogen that's here with the methyl group that's here on the alkyl halide, because you got to have an alkyl halide. That's what a ether synthesis is. It's the reaction of an alcohol with an alkyl halide in the presence of a base, right? So if we swap those two things out, what will we get? All this other stuff is just spinach, right? It stays intact. We don't touch it. So that's still there. I'm going to abbreviate that. The benzene ring is still there. This is still here. But now what should be attached to oxygen?
CH3.
The CH3. Thank you. Right? And that's your ether. All right. Let's see. Yeah, we got to come back. All right. So again, let me go back to here. All right. So that ether synthesis, these are the reagents you look for. You look for a base and an alkyl halide in the presence of an alcohol. Right. For your esterification, you look for a carboxylic acid in the presence of an alcohol with an acid catalyst. Right. With the acid chloride esterification, if you see an acid chloride in the presence of an alcohol, then you should know immediately that that's going to give you an ester. All right.
I have a question.
Go ahead.
Is the first one called trans because it's attacking the OH in the back?
No.
I want to know what's the difference.
Yeah, no, the trans part is just the two species. So you're transferring the alcohol, like the oxygen from the alcohol, and you're swapping it out with the OH of the carboxylic acid.
Okay.
When you see trans up here, it's not really dealing with stereochemistry. It's just a transfer.
Okay. Okay.
Great question. All right, so we know some reactions of alcohol, right? We know they make esters, we know they make ethers. We can also take alcohols and turn them into carbonyls. right? This is we're not gonna do any of these mechanisms because they're way, I don't say way too much, but that's a lot for the scope of what we're doing and with the time frame that we're doing it in. All right, so for the alcohol oxidation, you need an oxidant, right? So um, if you look at the bond order, primary, secondary, uh, you cannot oxidize a tertiary alcohol because what happens in the oxidation, let me cut this because we can talk about it a little bit. All right, you cannot oxidize a tertiary alcohol. I'm gonna show you why. Right, if you remember from part one, or from not organic, on CHEM part one. Let me crop this out. All right, if you remember from like CHEM, when we talked about oxidation and reduction, in CHEM, oxidation was like the loss of electrons, reduction was the gain of electrons. But in organic, it's a little bit different. So for organic, oxidation is to increase the number of bonds to oxygen, or decrease the number of bonds to hydrogen. All right, so you decrease the number of bonds to hydrogen or increase the number of bonds to oxygen. And reduction is the exact opposite of that. All right, so reduction would be to decrease bonds to oxygen and increase. So it's the inverse, right? It's the inverse of oxidation. Right. So when we talk about an oxidation of an alcohol, what we're talking about is taking that alcohol and doing one of those two things or both, increasing the number of bonds to oxygen, decreasing the number of bonds to hydrogen. If we're talking about a reduction, it's the opposite. We are decreasing the number of bonds to oxygen or increasing the number of bonds to hydrogen. We're going to talk about reduction down here too, because there's some reactions that are not on the sheet, but they fit in this section right here. So we look at the reactions, we can see immediately, let's take that first oxidation. We can use the Swern oxidation. Swern is just oxalochloride, I think, DMSO, right? So Swern oxidation is a specific set of reagents that'll take a primary alcohol and turn it into an aldehyde. And then chromic acid, which is the second one, second set of, that's, so you can use either one of those on a primary alcohol. Right, either one of them you can use on a primary alcohol. And it'll take that primary alcohol and turn it into an aldehyde. Now let me show you like what the basic premise of alcohol oxidation is and why you can't do it on a tertiary. So you know you got two hydrogens down here. I'm just going to draw them like that. And then I'm going to highlight what's coming off. So we're going to take this hydrogen and remove them. All right. So your oxidant in some way, and this is a very generic mechanism. So this is your oxidant. In some way, it's going to remove, let's say we have a bond here and some type of coordination here, right? It's going to remove the OH. Actually, let me do it the other way. It's going to remove this. Oh, let's do it that way. Remove this and that, right? So some type of way that oxidant is going to pull off those two hydrogens, called shuttling, hydrogen shuttling. So it needs to be able to take off each one of those hydrogens. And then in the process, what you get out of that is this. So you still have one. Let me color that one too. So you got one proton left. And now you have a double bond to oxygen. Right? So this is a generic oxidation mechanism. Right? So you think about a tertiary alcohol, why wouldn't this mechanism work on a tertiary alcohol? Sorry about that. Because this is your basic oxidation mechanism. You're taking off the proton off oxygen, and taking off the hydrogen on the CH bond, right? Most of the time it's in a form of a hydride. So why wouldn't oxidation work on a tertiary alcohol? Let me give you an example. I'm gonna put it over here. And I'll buy lunch to the first person who can answer this. For the first person who can answer. So let's say we take something like terbutanol. So we got terbutanol. Why can't we oxidize that up to a carbonyl?
Is it because it's too stable?
No, it's not it's not a stability argument. That's a good gander, but it's not based on the stability. What's the basic premise?
Because it only has one.
Go ahead.
One hydrogen.
You can't do the shuttling because you only have one hydrogen. That's exactly right. Who was that?
Amaria.
Amaria. This carbon right here doesn't have a hydrogen on it. So you can't remove, in order to oxidize a carbon to a carbonyl, this is the basic mechanism. You got to be able to take off one hydrogen from the carbon and one from the alcohol. And with a tertiary alcohol, you don't have that. Right? So there's no hydrogen in it. So if that's the case, it can't undergo that. You can't oxidize it anyway because a second reason, that's the main reason, but a second reason is that if you put a double bond there, how many bonds would that carbon have? Anybody? That's not for lunch though. That's just that's basic organic one. If I put a double bond between carbon and oxygen, what's the problem with that?
It has too many bonds.
Too many bonds. Right, it'll have 5 bonds to it, and that's not, you can't do that. Right. So for your oxidations, I know we only got like 3 minutes left, so I'm just want to run through them. So for primary alcohols, you want to use the Swern or chromic acid. Again, flashcards and repetition. That's what's going to help you remember these reagents. There's no magic way or shortcut way to get it. Right? You need to know the reagents and what they're specific for. So for Swern or chromic acid, they are specific for primary alcohols, and they're going to convert that primary alcohol to an aldehyde. Secondary alcohols is a different set of reagents with TPAP and NMO. TPAP is ruthenium, transition metal type catalyst, tetrapropyl ammonium perruthenate. I'll look it up, and I don't have to look it up, but I'll have the structure for you next time in case you want to know what that is. But TPAP and NMO works on secondary alcohols, right? So secondary alcohol, you want to convert it to a ketone, you use something like TPAP and NMO. And then if you want to convert the alcohol into a carboxylic acid, you use potassium permanganate, right? It's what you call a superoxidant. So it's going to oxidize all the way up to the highest oxidation state, which is 3 bonds to oxygen, right, for carbon. So if you do that, if you use the potassium permanganate, it's not going to stop at an aldehyde. On the primary, it's going to convert it all the way to the carboxylic acid. Right, and again, the reason there's no tertiary alcohols listed here is because you can't oxidize. Right, you can only oxidize primary and secondary alcohols. All right, we're going to stop there, and I'll post the notes and video and all that stuff. Like, any questions about anything?
Dr. Russell, you know, last semester you did a SharePoint at the end where we could upload our old assignments. Are you doing that again this semester?
Nope. Was that was too quick?
Dr. Russell.
Yep.
For one of the assignments, I think it was under the bonus assignment, I made a mistake and only submitted like 1 page. Can you reopen it so I could submit the rest?
Nope.
Okay.
Dr.
I'll add another attempt to that part.
Thank you.
And I'll consider the first request too. Consider it, but it's not guaranteed.
Thank you.
Like a lot of those assignments have been open for a long time. I just started closing them like last week, a week before last, all the way from February. But I'll think about the latest assignment, how to do that.
Dr. Russell,
Go ahead.
can you email me back, please, and thank you?
Hold up, don't get snippy now. I
ain't snappy, Dr. Russell.
I just sent you a thing in the chat. Did you see it?
Of course not.
Okay, so there you go.